Welcome to this NPTEL lecture on principles and techniques of modern radar systems. In previous classes, we have seen basic concepts of radar. So, in that we have seen unambiguous range, minimum range, then integration of pulses, then radar cross section, etc., etc. So, based on that, we will today do the first tutorial. We are calling it tutorial 1. Actually, the next lecture also will continue the tutorial, because there are several concepts. So, one by one we will do that. The first problem for this tutorial is this, that a ground based air surveillance radar operates at a frequency of 1.3 gigahertz. 1.3 gigahertz means radar people call it L band. Its maximum range is 200 kilometer for the detection of a target with a RCS of 1 meter square. Its antenna is a horn of 12 meter wide by 4 meter high. Its gain is 17 dB. The receiver sensitivity, we have introduced this term, is minus 100 dBm. The minimum detection range is required to be 300 meter. Now, based on this information, determine the following: the peak transmitter power, PRF to achieve a maximum unambiguous range of 200 K, average transmitter power, range resolution and azimuthal beam width. Okay. So, we will see this. If you read this question, it will be clear that there should be some equation which we need to solve to get one by one these parameters. So, what we will do, we will first write what is given. So, note down the problem, then we will write that what is given. So, I will say this is the solution 1. So, for problem 1, I am doing the solution. So, if you read, it is given that frequency, that means the carrier frequency is 1.3 gigahertz, then maximum range R max is 200 kilometer, then RCS of the target that is to be detected is 1 meter square. Now, antenna dimension is given. So, that, but the antenna gain is 17 dB and receiver sensitivity S mean, that is given as minus 100 dBm. You know that receiver sensitivity is basically the power, minimum power that is detectable by the receiver, so that it will say that a signal is present. Now, power's unit is minus 100 dBm. I think you know these conversions, that if we call 0 dBm, that means 1 milliwatt of power. So, accordingly you can calculate 100 dBm, minus 100 dBm, etc. The minimum detection range, that means R min, that also needs to be 300 meters. That means at least 300 meter beyond it should be able to see. So, we are asked that what is the PT. So, it is clear that we have done a modeling. So, the basic radar range equation, which that time we called a model, that will now help. So, we can immediately write the radar range equation. So, if you recall, the radar range equation was, or let me use this color. So, radar range equation was PR is equal to Pt Gt square. I am assuming this is the same antenna, that means monostatic case, lambda square sigma by 4 pi whole cube r to the power 4. Okay. So, but I have been asked Pt. So, I can now write what will be Pt. Pt will be just Pr 4 pi whole cube r fourth by Gt square lambda square sigma. Now, it is given that obviously this PR, this is minimum when we have the maximum range. So, that is called nothing but S mean. So, S mean is given. So, we can put that. So, here we can write that if we put in place of PR the S mean, then we will have to put in place of R max. So, both these values are given. So, that will do. So, that means we will now write that S mean is, it is given minus 100 dBm. So, that is 10 to the power minus 10 milliwatt, or we can call it 10 to the power minus 13 watt. So, I am trying to come to the SI units. Similarly, R max is given as 200 kilometer. So, that is 2 into 10 to the power 5 meter R max, and Gt is 17 dB. 17 dB is 10 to the power 1.7. So, that turns out to be 50.12. Now, lambda frequency is given 1.3. So, you can find out, because lambda will be 0.3 by frequency in gigahertz. This is the way. Other ways also possible, from that C by lambda, F, C and lambda, their relation, from that you can always get 0.23 meter, and sigma is given. So, then if you put all those, you get the value of Pt. So, Pt will, now you can put there. So, it will turn out to be 2.38 into 10 to the power 9 watt, or in terms of megawatt you can say 2380 megawatt, or you can say 2.38 gigawatt. So, this is the, remember, this is the peak power. Then let us go to part B. In part B, we were asked to find out what is the PRF. PRF to achieve maximum unambiguous range of the. So, we know that maximum unambiguous range and PRF, they are related. That relationship is R unambiguous is equal to C by 2 Fr. So, Fr is to be found out, unambiguous range is given, that 200 kilometer. So, you can, from here you can calculate Fr will be 750 hertz. Okay. Now come to part C. What is part C saying? That average transmitter power. You see that we have found peak power. So, we have seen that if we know the duty cycle, we can find out. Now, what is the pulse duty cycle? You see here directly it is not said, but indirectly it has been said. Actually, you see the minimum detection range is required to be 300 meter. That means that minimum detection range is R min. Now, what is R min? Basically, it is related to the pulse width that we have seen in the basic concept, that tau c by 2. So, from here we will get the value of tau. Tau will be 2 R min by the speed of light c. So, we know R min is 300 meter and c is 3 into 10 to the power 8. So, this will give you a pulse width of 2 microsecond. Okay. The moment pulse width is done, so and we have already found the PRF. So, we can find the average power. So, P average, we have seen that P average is P t into tau into Fr. So, now all these are available. P t is already we calculated, tau here and Fr here. If you put all these value, it will turn out to be 3.57 megawatt. So, you see that what was the peak power? It was 2.38 gigawatt and average power is reasonable, that 3 or 4 megawatt, 3.5 megawatt something. Okay. Now, next part is the part D, that what is the range resolution. Now, range resolution, roughly we said that it is equal to the pulse width. Later we will see that it is not pulse width, it is a fraction of pulse width, but for time being we can say that range resolution is approximately pulse width. So, range resolution is the that range distance according to A, that means the R min, what is called, sorry, not this, corresponding to the tau, what is the R min. So, that will be 300 meter, and the other one is azimuthal beam width. Actually, from antenna classes we know that beam width for an horn antenna in the azimuthal plane, this beam width, if we have it in degree, then there is a formula for azimuthal beam width. So, we can say that azimuthal beam width for horn, that is 70 lambda by d, where d is the maximum dimension of the horn. So, in our case we know the value of lambda, and d in our case is I think 12 meter. It was said that the horn is 12 meter wide and 4 meter height. So, this will be 12 meter and lambda is 0.23 meter by 12. So, this will turn out to be 1.34 degree. 1.34 degree is a typical radar azimuthal beam width. Okay. So, you see who helped us to get all these things? The thing is our radar range equation. You see, this is the second problem. Problem 2, a radar is tasked with detecting and tracking the moon. Suppose a radar is tasked with detecting and tracking the moon. Assume that the average distance to the moon is so and so kilometer, and its average radar cross section is, you see, huge thing, because several meters square. Now, why you can say that moon does not look so high, but if you see the illumination of the moon is quite bright to the radar, because lot of reflection comes from there. That is why it has a high radar cross section. Now, first part is compute the delay to the moon. That is, then what is the required PRF, so that the range to the moon is unambiguous. I want that this range, this 3.844 into 10 to the power 5 kilometer, that should be at least my unambiguous range. Now, then moon, what is moon's radar cross section in dBSM? Actually, this is in absolute value, the value is given. It is just that in dB scale to have you practice this, what is the convert it to dBSM. What pulse width you will choose to resolve craters of 1 kilometer diameter? It is an interesting question, that is anything to choose a pulse width, because I will have to find craters. You know, in moon various craters are identified by various moon missions. Suppose you have made a radar, or your country has made a radar, and you want to have at least craters of 1 kilometer diameter that you want to detect. So, what pulse width you will choose? Interesting question. And last part is, what needs to be the receiver sensitivity of the radar for a 100 megawatt peak transmission power. This is important, because suppose you cannot have more than 100 megawatt. Suppose you decided that I will have a 100 megawatt peak transmission power, then how good or what will be the requirement from your receiver. So, what needs to be the receiver sensitivity, how sensitive the receiver needs to be, so that it can achieve, it can detect the moon. Okay. So, please note down the problem, or these problems will be later shared with you. So, let us see and solve this problem. How to solve? Again, I think you understood that we will have to go to the radar range equation. So, now I will start with problem number 2. Now, here the first part is easy, that what is the delay. So, or you can say that time delta t for 2A travel. So, that will be 2 r by c, and you know distances are given 3.844 into 10 to the power 8 by 3 into 10 to the power 8. So, this will give you 2.56 second. That means, if you send a pulse, you will receive it after almost 3 seconds. So, you should remember that. That is why this problem is given. And what is the PRF? So, in problem 1 also we have done that. So, we will use this R unambiguous is C by 2 FR. So, from here we will find the FR. So, FR is 0.39 hertz. Okay. So, that is required, because otherwise you will not get, you have a large time for travel. So, that is why your PRF cannot be high, that is why it is less than even 1 hertz. Okay, these are reasonable things. Then that conversion, that convert the RCS given in meter square to dBSM. Now, remember what is the definition of RCS, because here to convert it to dB, which multiplier we should use, 10 or 20. I think you know that for primary quantities like voltage, current, etc., we use 20 multiplier as a 20 as a multiplier, and for second order quantities like power, energy, etc., we use 10. Now, what is sigma? Though sigma is not an dimensionless, but what is its a thing? That dimensionless, no? It is having a meter is the unit, but that does not give the clue. So, basically it is a ratio of power. If you see our definition of RCS, so it is the power that is radiated, etc. So, that is why we will have to take 10 log. So, this is important that you should remember that for RCS we will have to take 10 log. So, it is given 6.64 into 10 to the power 11. So, that will be 118.22 dB sm square meter. So, this all to done, then part D, what pulse width you will choose, that interesting problem, that resolve craters of 1 kilometer diameter. That means your range resolution, because craters will be in the direction of your range. So, range resolution should be 1 kilometer. Range resolution 1 kilometer. Now, what is the relation of that with the pulse width? I think we have seen that what that means the minimum travel time. So, we can say that this will give that tau is equal to 2 pi r by c, because this is the time that if you have this, so you can get this minimum thing. So, this will be 2 pi r, or this is capital R, you can say tau r mean. So, 1 kilometer means 10 to the power 3 meters by 3 into 10 to the power 8. So, this will be 20.94 microsecond. Okay. And last part is some calculation, that what is the receiver sensitivity. So, basically what is S mean? S mean we know is given by P t g t square lambda square sigma by 4 pi cube r to the power 4. This r should be r max. In this case, the distance from the moon, you consider that. So, if you assume that g t value is not given, so assume g t is 10 dB typically, or 10 dB and 10 are same. So, I can say 10 also. Let us say absolute value g t 10, and lambda let us say 10 gigahertz, 3 centimeter, that is 10 gigahertz. So, that is 0.03 meter. Then you will see that this comes to 0.14 microwatt. So, 0.14 microwatt or 140 milliwatt, it should be able to sense. Sorry, 0.14 microwatt, that means even less than 1 microwatt, it should be able to sense. So, it needs to be a very sensitive receiver. That is why generally radars from the ground do not generally observe it, because this is a real limitation. To have a radar sensitivity of this, is not so easy to very sophisticated receiver, etc. That is why you see that radar astronomy projects, that those which are observing various stars, etc., they are very costly. Generally, various nations are now, different countries are coming together, making consortium and having those things installed, etc. You see, an airborne radar has the following specifications: transmit power given, pulse width given, PRF given, antenna gain given, carrier frequency 10.5 gigahertz, receiver noise figure is this, system loss, propagation path loss, it is a free space model. What you are to do, find the SNR of the single echo from a 2 meter square target at 102 kilometer. Okay. And then it is saying that now suppose the radar integrates 2048 echoes with the integration loss of so and so, find the new SNR and the look time. That means, for how long time a target is looked by a radar. So, this is a problem on concept of integration of pulses. So, that we will see. The first part you will see that obviously from radar range equation it will come with those receiver noise figure, etc. That means, the loss, etc., needs to be taken into account. Correct. Let us come to, I think this is our problem number 3. So, we can say that this is the first part, that for a single pulse S by n, we know it is given by, from the again radar range equation, because S is the received power by n. So, P t g square sigma square lambda square sigma by 4 pi whole cube r to the power 4 k. This is the noise part, k t b. So, k t naught b, then you multiply with the noise figure and then any other system loss. So, this is the SNR expression for a single that we have seen. So, now you will have to put all those values. What are the given values? Given is G is given as 35 dB, that means 10 to the power 3.5. So, that will turn out to be 3162.28. Then lambda is 28.57 into 10 to the power minus 3 meter, that you can calculate from the given frequency of 10.5. So, it will be nearly 3 centimeter, a bit less than 3 centimeter, that is why you see this one. Then R is given, R is 102 into 10 to the power 3 meter. Then K, I think you know, K is Boltzmann constant 1.38 into 10 to the power minus 23 joule per Kelvin. Then T naught, T naught is the reference for noise calculations, reference temperature, that is 290 K. Then B, in this case B is said system loss pulse, B is not said. You see in the given specification, if we again see the given specifications, so nowhere the receiver bandwidth is said, but pulse width has been said. So, what can be done? We can do that, roughly we can say that it is the inverse of the bandwidth. So, if you do that, that means 1 by tau. So, that if you do, it will turn out to be 1.25 megahertz. Then FR, that FR is, it is said that receiver noise figure is 3.5 dB, again noise figure, so 10 to the power 0.35. So, that will be 2.24 absolute value, and system loss, other losses in various cables, various joints, etc., that is I think 1.4 dB. So, that means 10 to the power 0.14. So, if you put that, you get the value that we are looking for, that S by N single pulse, that will be 0.049 or minus 13.09 dB. So, you see that the noise is much more stronger than signal if we consider only one single echo. So, this is generally the radar receiver is not able to detect it because its sensitivity is not so high. So, that is why we need to integrate. So, now for integration, what will happen? So, part B is we are integrating. So, Sn integrated, that time the SNR gets multiplied. Meter square target. Now, only thing is with an integration loss of 0.8 dB. So, for integration, because if you do not coherently add, there can be a loss. So, you will have to take that, but I can say this will be in, this is the number of pulses to be integrated, number of pulses integrated, Sn single. If there was no loss, this is okay, but now there will be loss. So, we will have to take that Ls in absolute value. So, that will be nothing but 2048 into 0.049 by 10 to the power, what is that value? That value directly we can put 1.38. No, 10 to the power 0.16. So, that will turn out to be 69.43, which is 18.42 dB. Okay. And then the question is, what is look time? So, look time, I can say that for so many pulses, n number of pulses into what is the one pulse, how long it looks at a target, I can say 1 by PRF. So, for n pulses, this will be the time. So, this is 2048 into 1 by PRF is 250 kilohertz. So, if you do, it will be 8.192 millisecond. So, for this much time, the thing is looked into. Okay. So, we have seen 3 problems. So, one was remaining due to lack of time in this class we won't do. In the next tutorial we will cover that. Okay. Thank you.